Good to see you again. I hope you enjoyed our first day of this summer school and you had a great evening yesterday. And today you are ready for a new portion of science. And it is my distinct pleasure to introduce our next speaker, since we are working very closely with him for these years, and when he comes to our university, it is always fruitful time from scientific point of view. And he is an eminent researcher in nonlinear systems. And let me introduce Professor Alberto Isidori, professor from University of Rome, La Sapienza. He's going to talk about introduction to nonlinear system analysis, and in particular about geometric approach. So I give the floor to Professor Alberto.
Thank you. Thank you very much for the introduction, and I'd like to thank the organizer for having offered me this opportunity. It's always nice to teach, and it's always nice to get back to St. Petersburg, and of course, every invitation I get, I cannot resist, I come, because it's such a beautiful place to stay, and also such a challenging research atmosphere to be here and have discussions. Yesterday evening, we worked until 8:30, discussing a new paper. So, the organizer have asked me to give an introduction to nonlinear control, geometric viewpoint, and so I took it literally. So the first half an hour will be very, very elementary. So I beg your pardon if some of you already know these things, and if you find these things trivial or almost trivial. But then I could not resist to also include in the second half of the talk, include more recent arguments. So the idea is to give an overview of some of the results that can be obtained using this kind of approach to the nonlinear feedback design. Let me spend also one thing about the word geometry. Originally, geometry played a lot of role in the development of methods for feedback design for nonlinear system. Now, you will not see much hardcore geometry. You will not see something like tangent bundle or Riemann connections or whatever. But you will see some geometric concept anyway. Geometry is supposed to be coordinate free. On the contrary, you will see that my emphasis is on using spatial coordinates, because if you use spatial coordinates, things can be understood much better. But there are a number of geometric concepts behind that I will illustrate later on. I liked Romeo talk yesterday, which was a very nice historical perspective on adaptive control. Mine is not much historical, so you will not see names. I will say the names directly. It's a more kind of tutorial on how to control nonlinear systems in some special cases that are the cases that I've studied so far. So, where should I point it? Maybe it's something goes wrong. No, it
doesn't switch. Which slides?
Use it to switch before, but now maybe the battery is not. Okay, fine, perfect. So we consider in what follows systems described by this type of equations. X dot equal f of x plus gx times u, y equal h of x. This is not the most general class of nonlinear systems, but is general enough, and above all, it lends itself to the development of a rich theory. So x is a vector in Rn, f is a nonlinear function, we call it nonlinear vector field, gx is another nonlinear vector field, u is a scalar at the input. Most of the theory will be for single input, single output systems, even though by the end of this part one, we will see also how the theory could be extended to multi-input, multi-output systems. y is at the output. This is a function of x. So scalar u, scalar y, x is a vector, and everything else is nonlinear. And these functions are smooth enough so that we assume that derivative of any order exists. I hate singularities, so I prefer to stay with this general setup. Of course, this is an assumption, but it is reasonable to do this. So the idea is that if the coordinates in which the state space description is provided are appropriately transformed, then the equations that describe the system can be brought to a form in which the design of feedback law is suggested by the shape of the equation themselves. So it's facilitated. And as I said, this is a kind of contradiction with respect to the geometric idea, because I'm insisting on choosing coordinates, whereas geometry should be something like, should use more coordinate-free concept. But the choice of coordinates really helps a lot in design. And also this was the historical developments. People learned how to control nonlinear system after people understood how to choose spatial coordinates. In the case of a linear system, a change of coordinates consists in replacing the state vector x with a new vector x tilde, which is related to x by means of a linear transformation, x tilde equal tx, in which t is an unsingular matrix. If the system is nonlinear, we can no longer stick to linear change of coordinates. We have to use nonlinear changes of coordinates. So we have to allow nonlinear changes of coordinates. So a nonlinear change of coordinates, a transformation x tilde equal phi of x, in which phi is a map, nonlinear map, from Rn to Rn. And when such a map qualifies for a change of coordinates? Well, the map should be invertible, so we should be able to retrieve the old coordinate from the new one. So there must exist a map phi inverse from Rn to Rn such that the composition is identity. Phi inverse times phi should be x, and phi inverse x tilde should be x tilde for all x tilde. In the nonlinear case, the two identity are not both necessary. One does not imply necessarily the other in a nonlinear setting. So the map should be invertible, and since we assume that all functions here, vector fields, are differentiable, then the mapping should be differentiable as well. So phi and phi inverse should be smooth mapping. So they must have continuous partial derivative of any order. So this would be the general idea of a change of coordinates in a nonlinear setting. A transformation of this type is called the global diffeomorphism. So this is a technical name in differential geometry. If the transformation is defined only in a neighborhood of a given point, then the transformation is called a local diffeomorphism. Now we are going to change coordinates. To this end, we need a notation that became very popular, so maybe 90% of you already know this, and is a notation of derivative of a scalar valued function along a vector. So let lambda be a real valued function, so a function from Rn to R, a real valued function of x, and x is a vector field, so it's an Rn valued function of x. And suppose they are both defined in a subset U of Rn. Beginning with lambda and x, we define a new function for which we use this notation lambda sub x, L sub x lambda, and L sub x lambda is the function defined like this: d lambda I over dxi times xi, sum 1 to n. So this is a derivative, is a Jacobian matrix of lambda times the vector x. And this is called sometimes the derivative of lambda along x. Somebody calls also the Lie derivative, but I prefer to avoid this terminology because it's not based on anything. So it's the derivative of lambda along the vector x. It's a classical operation in elementary calculus. If y is another vector field, we use this notation Ly Lx lambda this will be the derivative of the function Lx lambda along y. So starting with lambda, we can take a derivative along x and take a derivative along y. And we can use it recursively. And Lx k times lambda is a derivative of the function Lx k minus lambda along x. So we can do repeated derivative. And this will be needed because we will have to compute repeated derivative of the functions that describe the system. Now, with this notation in mind, there is a very simple definition. The nonlinear system that we saw in the previous slide is said to have relative degree R at some point x0, so the notion is attached to a point. So the system is said to have relative degree R at some point x0 if the repeated derivative of H, the outer map, along F k times, and then along G one time, is identically zero, is zero for all x in a neighborhood of the point, and for all k up to r minus 1, actually up to r minus 2, so this is strictly less than r minus 1. And then the next derivative, so for k from 0 to k minus 2, we have functions that are identically zero in a neighborhood of the point. But then if we do one more derivative, so we take LF R1 minus 1 time, R minus 1 time, at the point x0 is non-zero. So this definition of relativity at a point. The reason for the terminology relative degree is that if the system were linear, this would correspond to the difference between the degrees of the denominator of the transfer function and the numerator of the transfer function. This is why it's called relative degree. Some of the terminology is borrowed from the similar results for linear systems. This concept is a local concept. So R may depend on the point. This is clearly in the definition. And so the value of R may be different points. And there may be points where the relative degree cannot be defined. How can this be the case? Well, this occurs if if you look at this sequence, which is a sequence considered here, LGH, LGLFH, LGLF to the KH, the first function, which is not identically zero, then is zero exactly at the point. If this happens, we have a singularity, we cannot define relativity at that point. However, since f, g, and h are smooth functions, the set of points where the relativity cannot be defined is an open, where the set of points where the relativity can be defined is open and dense. So if you take the closure of this set, we get the entire variance. So the singularities are a set of zero measure. Well, we will abandon soon this story of the singularities because we will make assumptions that guarantee the existence of the relativity at every point and the same value at every point. Okay, so with this in mind, what is this notion good for? This is a calculation very elementary that everybody should do in his or her lifetime. Suppose that the system at time equals 0 is in the state x0. And let's calculate the value of the output and of its derivative with respect to time. Yk is the derivative of order k at t equals 0. So y0 is by definition h of x0. Remember that the system is this. Build this system. I can just rewrite this system just to help you. Let me rewrite this system here for convenience. So the system is x dot equal fx plus gx times u, y equal hx. So the output at 0 is h at 0. x0 was x0, so we have this. The first derivative, this function is a composite function. Y of t is h of x of t. So when we take derivative, we have use the chain rule. So Jacobian of h with respect to x times dx over dt. Jacobian of h with respect to x. dx over dt is x dot, so it's this expression here. So now we discover why we have introduced this notation, because this product, dh dx times f, is this, L sub fh. df dh times g is this. So the notation is useful to represent this derivative. At time t equals 0, y1 at 0 is this number. It's absolutely trivial. We put x0 here, x0 here, u0 here. And this, we see that if r was equal to 1, this quantity is non-zero by definition, if you look at the definition of relative degree, definition given here. If r is equal to 1, this function is already non-zero. R equal to 1, LGH, x0 is non-zero. So the first derivative is a affine function of u0. u0 appears in here. Otherwise, if r is larger than 1, if t is small, xt remains in a neighborhood, and therefore this function is identically 0, because we say that if r is larger than 1, this function vanishes for all x's near x0. And therefore the first derivative formally is independent of u. y1 prime is this, is another function of x. And now we keep going. So let's compute the second derivative in that case, in the case r is larger than 1. The second derivative is, we have to use the, actually here I believe I forgot something, there is a partial of this. Transparencies are never perfect, there is always misprints. So there should be a Jacobian of this times dx over dt. So it's Jacobian of x, Jacobian of LFH times x dot, as in this calculation. So we replace the Jacobian of x with the Jacobian of LFH times x dot. And now this notation is correct. This is the second derivative of h along f, the derivative of LH along g. So we have this expression. So at time t equals 0, the second derivative of the output, if r was larger than 1, has this expression. So if r is equal to 2, this number is non-zero, so the second derivative is an affine function of u. And you understand that we can continue in the same way. So if r is larger than 2, then for all t near t equals 0, we have this quantity 0. The quantity here is 0. And therefore, the second derivative is no longer explicitly dependent on u. It's a function of x only. We continue in this way, and we have formulas like this. The derivative of y at k times is a function of xt only if k is strictly less than r, and this occurs for all t near t equals 0. But the derivative of order r, if we go one step higher, at 0, is a function which is now explicitly depending on u, because this number is non-zero by definition. Thus, the integer r is exactly equal to the number of times one has to differentiate the output at time t equals 0 in order to have a value of u explicitly appearing. So we see from this calculation that yk for k between 0 and r minus 1 are function of x only. And therefore, we believe that these functions, h, lfh, lfr1 minus 1h, must have a special importance because they are related to the outputs and derivatives. They are not affected by the input. And as a matter of fact, such function can be used to define, at least partially, a local change of coordinates around x0. And this is what is written in this proposition. Suppose the system has relativity r at some point. Then necessarily r cannot exceed n. This is the result of the definition, consequence of the definition. If r is strictly less than n, it is always possible to find n minus r more function, in addition to the r function that we have there, such that, we label this function as psi1, psi n minus r, such that this list of functions defines a change of coordinate. Here we have r functions from here to here. Here we have n minus r. The total is n functions. So we have a map from Rn to Rn. And this qualifies as a local change of coordinates. Because one can prove that the Jacobian matrix is non-singular, and therefore, using differential geometric concept, one can prove that this defines a local change of coordinates in a neighborhood of the point. Of course, if r was equal to n, there is no complementary set. The set of h, lf, h, lf to rn minus 1h suffices to define a change of coordinate. If r is stricter than n, then we have to complement and complete a change of coordinates. The value of the new function can be fixed arbitrarily, and this is a nice feature. One can prove that it's always possible to find the function psi in such a way that Lg psi is 0 in a neighborhood of the point. This is the additional bonus. I will comment on this bonus later on. So this is the basis of changes of coordinates. Now the description of the system in the unit coordinates is found very easily. Now define z is a vector consisting of the z1, z2, zn minus r. This is a complementary set of coordinates. And we define xi as xi1, xi2, xi-r. So the total number is n, as you see. These functions have a clear meaning. H, lf, h, lf, r minus 1h. These functions are more fuzzy because it's just some complementary set. And x tilde, the new state, will be the column of the zi xci. We call it phi x. This is the definition of change of variables. Now, if we now bear in mind the previous calculation, we realize that, for instance, the xi1 dot, the derivative of xi1 with respect to time, is xi1 is hx. So we have a Jacobian of hx times x dot. We already seen this before. This is equal to LFH because of our previous construction. Remember the construction that we had before. This construction here is the same. Nothing new. So we have the derivative of xi1 with respect to time is LFH. But this is the second coordinate, so we get xi1 dot equal xi2. And then the same way we get xi2 dot equal xi3. This is why these functions are very nice to be used as new coordinates. And then xr minus 1 dot is equal to xr. But here we have to stop because we go to the next derivative. Xr dot is a function of x, which is LFRH, plus a function of Lg, Lf, R1h times u, and this function is no longer 0. So we have the input explicitly appearing. So this is the description of the system in the new, so long as the xi coordinates are defined. On the right-hand side of this equation, of the last equation, we have still x here. But if you want to do our homework completely, we should remember that x is a function of the new variable, because x should be replaced by phi inverse of the pair zxi, which are the new. The pair zxi is the x tilde, x is phi inverse of x tilde. So we have to replace in here, in lieu of x, we should write phi inverse of zxi, and we end up with a function that depends only on z and xi, and also here we end up with a function that depends only on z and xi, and therefore we can write the equation in this form. Now this is more consistent because we have new coordinates on the left-hand side and the right-hand side. But this function b is non-zero because this quantity was precisely this quantity, and this quantity was non-zero in the neighborhood of the point. So do you take advantage of the fact that this is non-zero? So this much about the coordinate xi. The coordinate z, we cannot say anything special because the psi have no special meaning. They're just a complementary set. So Ci dot is the Jacobian of psi with respect to x times x dot. We run the standard notation LF. We do this calculation. The standard notation is LF psi, LG psi. And since we say that we can choose a psi such a way that this is 0, we remain with an expression that does not involve u. So if we organize all these functions in a vector, we obtain an expression like z dot equal f0 zc, very generic up to this point. So the only real advantage was in getting this chain of integrations here. But this is good enough to do some control theory, control design. In summary, in the new local coordinates, the system has this description. There is an upper set z dot equal f0 zc, and then there is a chain of integration, then there is another expression here, and I have the u appearing. Of course, we have to specify also how the output is related to the new coordinates, but output was hx. Hx is the first new coordinate, c1, so this is completes the change of coordinate. These equations are said to be in a strict normal form, and they are useful in understanding how certain problems can be solved. Why the word strict? I use the word strict to stress the fact there is no u in the upper equation. If we don't choose the psi, which we are free to choose the psi not to satisfy the condition Lg psi equals 0, then in the upper equation we should expect the u. So this depends on our choice of the complementary set. If we are lazy, we don't want to spend time in finding psi such that this is 0, then we end up with an equation in which the u also appears. And we call this non-strict normal form. The fact that the existence of strict normal form is a thing that can be guaranteed only for single input, single output system. This is why it's important to bear this rather more general structure in mind. Okay, if you don't want to see this extended notation, there is a simple way to represent it. Let's define by A sub r, B sub r this triplet. This is a shift matrix of dimension r. This is this vector, and this is the row. This triplet A, B, C is sometimes called in prime form in the literature on linear systems. If I had a linear system having this A, B, C, the transfer function will be 1 over s to the r. With Ada-Sat notation, we can, they can represent these equations in this form, which is rather simple. The top equation is the same. Here we have xi dot equal arc, because there is a shift. The only thing that is not shift appears in the last equation. And this is why here we have BR, only the last equation, QZC plus BC times U, and Y is equal to CR. So this is the strict normal form. The non-strict normal form will be the same, but we would have G plus G0 times U on the top equation. So this is not so bad. So you see, system has some linear feature to a certain extent, because this is a linear piece. In part is linear, in part is nonlinear. There are assumptions are known under which a normal form exists globally, because so far all the theory was local. And fortunately, one can determine whether or not global normal form exists. And this is the next result, which is a little bit more technical. If we have a pair of vector fields x and y, we define by, I think there is a square bracket missing, the Lie bracket of two vectors, y and x, is defined as Jacobian of x with respect, Jacobian of x times y minus Jacobian of y with respect to x. So the second one comes first. Jacobian of x times y minus Jacobian of y times x. And this new vector field is called the Lie bracket of x and y. Now, define G star as Gx defined by this quantity, divided by this quantity. And F star is F minus G times this quantity here, And recursively, we take the Lie bracket of G star along F. So x0 is G star, x1 is F star G star, x2 is F star x1, and so on and so forth. So the proposition says that if these vector fields are complete, then one can find the function psi such that LG psi is 0, and the map is globally defined diffeomorphism. What does it mean, vector fields are complete? This is a simple notion. A vector field is complete if I look at the differential equation x dot equal capital XX, x is an Rn, then this differential equation has solution for every initial condition x0 defined for all t on the real axis. So if this differential equation has a solution for every initial condition and for every time, then the vector field is said to be complete. And actually, these solutions can be used to find the complementary set of coordinates. It's a very technical differential geometric result, but it's good to know that there are conditions under which a global diffeomorphisms exist. So if f0 is equal 0 and h0 is equal 0, one can pick the psi in such a way that phi0 is 0, and therefore the diffeomorphism preserves the equilibrium. As a consequence, in the new coordinates, z equals 0, xi equals 0 is an equilibrium, as x equals 0 was an equilibrium in the old system. And therefore, we have to have f0, 0 equal to 0, q0, 0 equal to 0. Because if you put u equals 0, then z xi will be an equilibrium if and only if f0, 0, 0 is 0, q 0, 0 is 0. Okay. So it's good to know that the equilibrium is preserved. So this much about the change of coordinates. And this was the kind of elementary part of the analysis. Now, now I will study some apparently independent problem, and later we will see why this is important. The concept of zero dynamics. Let me do the following experiment. I would like to compute all the pairs. Now, remember that we have a system like this. We have a system like x dot equal fx plus gxu, y equal hx. I have assumed that f0 is 0, so there is one equilibrium at 0. I have assumed that h at this equilibrium was 0. This assumption only requires that we have at least one equilibrium, then we shift the variable to this equilibrium. This assumption is not expensive at all, because if at the equilibrium this is not 0, we shift the output so we can fit this condition. Now, observe that if I have a system like this, and I put ut identically 0, then yt will be identically 0. This is trivial, because if I put yt 0, I am in an equilibrium, so x will remain at 0, so y will remain at 0. For all t. For all t. So this is a particular pair, x0 equals 0 and ut identically 0 is a particular pair of initial condition and input initial condition x0 and input ut such that the corresponding output is dead. Y of t is identically 0. This is a trivial thing. Now I would like to find all possible pairs, not just this one. I imagine that there are many other pairs with this property. There have to be pairs because the output is determined by the input and initial condition. I would like to look for all possible pairs of initial condition and input for which the output is identically zero. Why I'm doing this? Well, the idea of zeroing the output is common in control because it's related to the problem of tracking. But anyhow, I prefer to remain on a more abstract conceptual setup. So we see from the above construction that if y of t is identically zero, then all these functions will be identically zero because this function, this is y of t, which is zero. This is the first derivative, but the first derivative of a function which is identically zero, so this will be identically zero. This will be identically zero. So if y of t is zero, we have a bunch of functions that are identically zero. And remember that this was the derivative of order r minus 1 of the output. If you look at the next derivative, we get this. But if this derivative was identically zero, then also the next derivative is identically zero. So we have all these conditions. So if the output is zero, all these constraints must be respected. Now, some geometry, since the title of the lecture was Geometric Concept, some geometry. Look at this set, the zero set of all these functions. The set of all x for which h is zero, LF h is zero, LF r minus 1 h is zero. This set is a smooth surface, I should call it a smooth manifold, of codimension n, because we have a codimension r, because we have r independent functions that vanish at this point. So it's a smooth submanifold codimension r. And moreover, it is, I will do the calculation on the blackboard, since I want to do some geometry. If we consider this control, u star of x, like this, which is the division of this by this with a negative sign, the vector field f plus g star is tangent to z. What does it mean? Let me call this star is a zero set of a certain number of functions. So this star is a set of all x's in Rn such that hx is zero, LF hx is zero, LF to the r minus 1 hx is zero. Let me denote this set of functions by m. So we have a function mx, which is zero. Here, this m has r rows. So if y is zero, then necessarily we have to have m xt is zero. Okay. This, since we have this identity, let's take the derivative of this identity with respect to time. Because we have a function which is identically zero with respect to over the time, so the derivative will be zero, so the d over dt of mxt will be identically zero. But this derivative, if we use the chain rule, we have dm over dx times x dot. This will be identically zero. So the vector x dot will be in the kernel of this Jacobian. In turn, f is x dot is fx plus gu. be 0. Now, if we put u equal to this quantity u star here, the last element of this function will be 0, and therefore we had this condition fulfilled. So this vector, which is the velocity, this is the velocity of xt, because it's x dot, the velocity will be tangent to the set mx equals 0. So the set mx equals 0 is a surface. If x remains in the surface, which is the constraint that we deduce from this, then the velocity vector, which is the tangent vector to this, x dot, should be tangent to the surface, and this is the tangency condition. So if we use this control, which is the function of x, we get a vector field which is tangent to z star. This star is the 0 set of this is the set z star. And the terminology is that the set is invariant. A manifold is invariant with respect to a vector field if the integral curve of this vector field remain in the manifold if we pick initial condition in the manifold. And invariant means that they remain in the manifold for all future time, for all past time. Otherwise, we should say positive invariant, negative invariant. So we conclude that the output is identically 0 if and only if the initial condition is taken on the manifold and ut is u star of xt, where xt is a solution of this x dot equal f star x. So a solution of x dot equal fx plus, here we have plus gx times minus lfkx divided by lg lfk minus r minus 1 hx. This is the system defined by for all x's. But if we pick x, if we pick the initial condition on this manifold, then the integral curve will remain on the manifold. This is it. So the system is defined for all x's. But it makes sense to speak of restriction of this system to the manifold M, because we know from this analysis that if we pick initial condition in Z star, then the trajectory remains in Z star. So the restriction of x dot equal f star is this vector field. X dot equal f star of x to the invariant manifold Z star characterizes all internal dynamics that occur in a system if we pick initial conditions and input in such a way that the output remains identically 0. So all internal motion that are compatible with the fact that the output is 0 are obtained by taking initial condition in this star and looking at these trajectories of this vector field. You see, this is a really coordinate-free approach. And now you understand, in the next slide you will see why I prefer a coordinate-like approach, because this analysis is less difficult if you look at the coordinates. In the coordinates of a normal form, the set Z star is a set where all h are 0, but these are xc1, xc2, xcr. So the set Z star in the new coordinate is a set where all the xi are 0. The restriction of x dot equal f star to Z star is the manifold, is this system, because we take, if we set xi equals 0, we remain with this equation. All the other are 0. So we remain with this equation here, z dot equal f0 z. So this characterizes the restriction of u x dot equal f star x at the manifold z star, which is invariant by construction. The restriction of u star to the set d star is this input here. Because, this q was lf to the power r h. This was lg, lf to the power r minus 1 h. We put 0 here, 0 here. Sorry, there is an extra parenthesis. So the dynamics of this is in coordinate free terms. Or, what is the same, dynamics of this, sorry, there is a 0 missing here, are called the zero dynamics. It is nice to observe that this construction demonstrates the equivalence between the open loop characterization. Let me just comment this. Here I was looking for all possible inputs, for all possible pairs, input and initial condition giving rise to zero output. So my experiment was like this. I imagine that the output is dead. Y of t is dead. And I look what are the compatible initial condition and input. This is an open loop formulation because I go back from the output to initial condition and input. But then I discovered that the input that guarantee this, the input that guarantees this are precisely feedback. Because this ut is nothing else than the result of my minus Lf to the power R Hx divided by Lg Lf to the power R minus 1 Hx. So this is a feedback. So we call it U star x. So the open loop input that guarantees zero output are naturally implementable as feedback. Of course, we have to pick the initial condition appropriately, which is on the manifold D star. So the dynamics characterize the forced state behavior of the system when input and initial conditions are chosen in such a way as to constrain the output to remain identically zero. So why all this burden about computing this? You will see in the forthcoming slides. First of all, let me make a link. The name, why zero dynamics? Zero dynamics is motivated by the fact that I'm looking at the internal dynamics consistent with the fact that the output is zero. This is one motivation for the term zero dynamics. But there is another motivation which we could borrow from the linear system theory. If the system were linear, the function f0 would be linear, and q would be linear, and b is a constant in the case of a linear system. So in the case of a linear system, the normal form looks like this. Some linear function of z and xi, AR, BR, CR, as we have seen before, linear function of z, xi times u. An easy calculation that you could do as a homework is that the transfer function of this system looks like this. I never found this in books on linear system theory, but this is a very powerful formula. So the transfer function is, the denominator is a characteristic polynomial of A, the entire A. So A will be F, G, BH, BRH, and ARB, so the characteristic polynomial of A. The numerator is the characteristic polynomial of F. And B, the high frequency gain, is this coefficient here. So this formula can be proven very easily. A couple of pages of calculation, you can prove this formula. But apparently, you will not find this formula in books on linear system theory. I don't know why. From this, you conclude that if we have a system, now you see the eigenvalues of f are the zeros of the transfer function. So if the system were linear and minimal, then the zeros of the transfer function will be the eigenvalues of f. This is why we call this zero dynamics, because in the case of a linear system, the dynamics that we obtain, which is this, is the linear dynamics whose eigenvalues are precisely the zeros of the transfer function. So this is the second reason to use the terminology zero dynamics. Okay, now we move to something a little bit more elaborate. It has the link, the new idea is to have a link with the inverse system. Inverse systems were overlooked for a long time, or were not studied, considered enough, especially in the feedback design problems, until in a paper by Morse that was quoted yesterday, Sontag and Lieberson, they showed that it's important to look at the properties of the inverse system also when doing stabilization of a nonlinear system, especially in the case of multi-input, multi-output system. So another property associated with the notion of zero, the transfer function, of a single input, single output linear system, is the fact that the zeros characterize the dynamics of the inverse system. The inverse, if we invert the transfer function, we know that the zeros become poles. So the zeros characterize the dynamics of the inverse system. And the inverse system is seen as a system that is able to reproduce the input starting from the output that this input has generated. So you give me the output, I'm able to reconstruct the input. Now, in the nonlinear case, this exercise can be done relatively easily. Suppose we have a normal form. We have to go back to our normal form. The output is xc1. So this is xc2, xc1 dot. xc3 is xc2, c2 is xc1 dot. xc3, xc1 double dot, and so on and so forth. So all the xi here are the output and derivatives up to order r minus 1. This is the derivative of order r of the output. So the input u can be expressed as a function of derivative of the outputs and the variable z. The variable z also depends on the derivative of the output. And therefore we have, if we can easily invert the system here, discover how u is related to the y and to some internal state, which will be the internal state of the inverse system. So with this in mind, we immediately build the inverse system. The inverse system is like this. Z dot is equal f0 z, and here we have the vector consisting of y and all its derivative up to order r minus 1. So this y bold is the column of y, y prime, y r minus 1. So this is a system with internal state z driven by outputs and derivative. And this is y, u, the input, expressed as a function of z, the internal state, and outputs and derivative up to order r. There's one more derivative function. So this is the inverse system. And you see that the internal dynamics are those of f0 zy. So the inverse of the internal dynamics of the inverse system coincide with the zero dynamics defined above. So there's another reason that that convince ourselves that this concept is important and fits very well with a number of concepts that are familiar in the linear system case. I also want to note that if this is in particular important for the case of multi-input, multi-output system, if the normal form was non-strict, here we have to add another piece, G0, times U, but U is this. So it's much more complicated. Remember that, let me just comment a little bit, that if the normal form is non-strict, we have the top equation is z dot equal f0 zig c plus g0 zig c times u. And I say this is a particular non-strict normal form normally occur when the system has many input, many output, as we will see in a moment. If the system has only one input, one output, one can choose a z in such a way that this is 0, but this choice is only possible for single input, single output system. So this is the top equation when the system is in non-strict normal form. Now, if we look at the problem of inversion, this becomes y bold r minus 1. So this means that y bold r minus 1 is this vector y prime to the order r minus 1. So this vector becomes y bold 1. This vector also becomes this, but u is always obtained by the last equation. U is always this. So the u here should be replaced by this. So these are the dynamics, the internal dynamics of the inverse system if we have chosen different z variable, namely z such that this g0 is non-zero. So this is important to bear in mind. So in general, we expect that the dynamics of the inverse system have such complicated expression, but this is because we are not choosing the special z for which this will be 0. Okay, so we go ahead another half an hour, so make a break at 10:30, 11:30. The coincidence between zero dynamics and dynamics of the inverse is limited to the single input, single output system. For multi-input, multi-output nonlinear system, the link is more subtle, and this requires more calculation. This is essentially due to the fact that while the concept of zero dynamics determines only seeks to determine the dynamics compatible with the concept that the output is 0, when we look at the inverse, so when we compute the zero dynamics, we have in mind the idea that the output is 0. This was the experiment that we have done. If we look at the inverse system, we want to determine the input starting from any output, so the output is not necessarily 0. So it is only a coincidence for single input, single output system that we get the same dynamics. In general, it will be different. So as a consequence, the computation of the zero dynamics and the computation of the inverse system, whenever this is possible, are not equivalent, and the latter is only possible under substantially stronger assumption. And if you want to know this, if you want to know more about this, you have to look at the literature. It's a little bit complicated. In a book that I wrote recently, there is a 30-page chapter to explain how to compute the inverse system and to compute the dynamics of the inverse system. So the computation of the zero dynamics is based on the extension of a classical algorithm of Wanham for the computation of the largest controlled invariant subspace in the kernel of the output map, while the computation of the inverse system is based on an extension to the Hirschhorn and Singh of the so-called structural argument that was introduced in the 60s by Silverman to the computation of the so-called zero structure at infinity. This is not new stuff. Actually, what is new, which you will see a little later, is the use of this concept in feedback design. So the analysis of multi-input, multi-output nonlinear system was achieved to a kind of satisfactory degree of sophistication in the 80s, but then a kind of blackout occurred, and people were not interested anymore. They're rather interested in multi-agent systems or kind of similar stuff. But recently there's been a revival, and lot of problems that have been left open now are being solved in these days. Arya's not here, yes. But then I object that I don't have the transparency here. I have a transparency showing the occurrence of, if you Google the terminology zero dynamics, you see the growth of over the year. Now there are probably tens of thousands of papers that use the terminology zero dynamics, whereas clamped zero dynamics, I'm afraid, has remained. Now, for people who doesn't know, Aryan, I think, was studying similar things and they used the terminology the clamped dynamics, but then the terminology zero dynamics is established as a brand name. Just Google zero dynamics, and you see how many papers appear. Okay. Now, so far we have considered models of the system, and with this fixation of choosing spatial coordinates. Now, what are these spatial coordinates good for? Here is the most trivial application that we can see. Consider again this system here, the system that we had before, which we know we'll write in like this. Now, this is a linear version. The nonlinear version is this. Yes. So this is a system in normal form. And nobody can resist to, since B is non-zero, I think nobody can resist to choose U so as to suppress this part, to make this linear. I think is irresistible, the temptation of taking U equal 1 over B minus Q plus another function. Cancel all the nonlinearities in this part. This is possible. Why not? We will see why not. So if we take this input, this control, let me just repeat it for you. We have our system. Z dot equal F0 ZC, Xi dot equal AR Xi, the shift matrix, plus BR Q ZC plus B ZC U. These quantities are over 0, so we can choose a U that changes this into KR Xi. We can do this. Just use the control written just use this control. Divide by B, cancel out Q, replace by KR, maybe add some extra input V if you wish. Y was equal to CRX. So this operation makes a piece of a system fully linear. And this was the first discovery, 1979, I think, in the study of nonlinear systems, that the system can be made partly linear by choosing this, I would say, naive control law. The system can be made partly linear. AR-BR is a controllable pair, because it's a prime form, so we can assign the eigenvalues. So we have a stable linear system between the new input V and the output Y. In fact, this feedback law has made the system partially unobservable, and all nonlinearities are confined to the unobservable part. The Z variable is unobservable in this. Feedback can destroy observability, and this particular feedback has destroyed observability. So what? If we use this feedback, we assume that Z is available, so we don't have to worry about observability. So as destroyed observability, and this behavior is linear and stable. This control law is clearly naive, is non-robust, as it relies upon the self-cancellation of possibly uncertain terms. And I remember when this was discovered, everybody said, well, this is a nice technique, but of course it's not usable because no one can exactly. Here we have two drawbacks in this feedback law. First of all, that we need the entire state. So this is a full state feedback. We need to know Z and C. But we need to know B and Q accurately, otherwise cancellation cannot occur. And we all know that cancellation is not a good design technique. So this is not robust. But it can be made robust. So after, this result was discovered in 1979, more or less. This result is called input-output linearization. And it was understood only recently. It was a paper by Khalil and Freidovich, I think, 2008, in which they have developed a robust approach to this. And the multivariable version of this has been discovered only very recently. There is a paper that yesterday I received the final letter from Astolfi of acceptance of this paper, in which there is a general approach for multi-input, multi-output, not having vectorality degrees. It's very sophisticated techniques by means of which the multivariable version of this feedback law can be robustly implemented. So the work still in progress, but it took almost 40 years to go from this naive idea to the robust version. And this because the attention of the people was distracted by multi-agent system and so on and so forth. Huh? Robust means that we don't need to know Q and B accurately. We don't need to use Z and C. Continues to be not robust with respect to measurement noises, as we will see, but the idea is that we can ignore Q and B. There is some high gain behind this, but the high gain is only in the observer. So the final result that I will comment in a moment is that we keep the performances of this. So we have robust, and the KR here is not high gain. KR just assign the eigenvalue. You assign the transient that you want. The whole high gain is in the observer. And of course, the drawback is that since we use a high gain observer, then this is sensitive to measurement noise. But this is the only drawback of the technique. But this will be clarified in a moment. Okay, so this much about input-output linearization. So I'm anticipating what we will see after the break, how to make it robust. But let me discuss one more term. So one more thing, which is very important. If we have a system like this, what happens to the internal dynamics? So we have a very nice linear system, even though it is naive, it's non-robust, but we have a very nice linear system between input and output, but we still keep some internal dynamics. So the internal dynamics may go wrong. So we have to assume that something is nice here. Otherwise, we are in trouble. For the time being, so before we get to the robust story, observe that the system has a structure of a cascade of two systems. You see, this is a system. The bottom system is a completely autonomous, is a self-contained system with input V, state Xi, output Y, and Xi drives the upper system. So this is a cascade structure. So the lower system is this, and the state drives this. So it's a cascade structure. Therefore, since we want to achieve this result with internal stability is not just stability of Xi, it's also stability also of Z, we have to look at the asymptotic properties of this system, of the second system with the cascade. So the cascade is like this. I remember that when we first discussed this thing, we called this a sink. So this is z dot equal f0 z xi. This is xi. The output is independent. This is v, and this is linear. This is a kind of sink. Because we have made it a sink using this particular feedback. But we have to reflect a little bit about the internal dynamics of this. Linear systems with no zeros in the red-half plane are traditionally called minimum phase systems. And this is in view of certain properties of the body plot. Don't ask me precise interpretation, because this is a terminology that dates back to the 30s, that was introduced by Bode. In view of this interpretation, we say that a linear system with zero dynamics asymptotically stable we call minimum phase system. So we borrow this terminology also in the linear case. So this terminology has been somewhat abusively, but with the clear intent of providing a concise characterization, borrowed to classify the dynamical properties of this system. If the system were linear, you have z dot equal fz plus gxc, and if the zeros are in the left half plane, this system is stable, and we call it minimum phase. This is a standard terminology for linear systems. Now we borrow the same terminology, so if this system, as a nonlinear system, has some nice stability property, we keep calling it a minimum phase. So just a terminology. There is no such thing as a phase, just a terminology. So here is the definition. Consider a system for which f0 is equal to 0, 0 equals 0. Suppose a system has a relative degree and possesses a globally defined normal form. Now we know what are the conditions. Then we say that the system is globally minimum phase if the equilibrium z equals 0 of these dynamics, so the internal dynamics arising when output is 0, are globally asymptotically stable. It's globally asymptotically stable. So this is definition number 1. We set xi equals 0, and we get a system which is globally asymptotically stable. And this is the one which is more recognizable comparing with the linear system. But definition number 2 says the system is strongly minimum phase, and this is a more important property. If this system, in which now we have xi, is input to state stable. Now, and this is we need to say what input to state stable means. So now we are studying this system here, z dot equal f0 z xi. If xi equals 0, we look at global asymptotic stability. If xi is non-zero, we look at a more sophisticated property of a system that has a state and an input, and this is called input to state stability. This was a concept that was introduced by Sontag in the late 80s, which is an extension of the Lyapunov theory to system having inputs. And here I have the definition of the property. This system is input to stay stable if for every input xi now is viewed as an input. If for every input and for every initial condition, the state is bounded by an expression like this. Now let's ignore these sentences here, just look at the formula. So the state at time t is bounded by a class KL function. A class KL function, a function that decreases asymptotically to 0 with time and increases with the initial condition. So this is a kind of homogeneous term that is going to decrease to 0 as time tends to infinity. But also we have to bear in mind the effect of the input, and the z at time t is bounded by a function which is a class K function, so increasing function, of the subnorm of ct over the interval, and this should be c tau. The subnorm of c tau over the interval 0t. So we, for instance, this is ct, this is norm ct, c tau. The norm has, well, like this, and we look at the sup norm as this number here. This is t, so this sup norm of xt over the interval 0t. And this should be true for all t. So the state is bounded by a decaying function of the initial state and a possibly increasing function of the input. And if this occurs, the system is said to be input to stay stable. And of course, since I say that system is strongly minimum phase, if this system is input to stay stable, then this definition applies to this. Well, of course, it would be nice to have time to discuss this notion. It's very important. And in practice, this notion really changed the way in which people studied stability of interconnected systems, because it's very much suited to study stability of interconnected systems. But let me mention one interesting fact, that the notion of input to state stability, this notion is very cryptic, because how can you determine that this is true or not? You have to compute solutions for every initial condition, for every input. The system is nonlinear, very complicated. Well, there is a test, which is an enhancement of the Lyapunov test that determines when this is true. So in the test, let me write the test for you here. If I have a system like this, x dot equal fxu, which is like this. This is our special case. X was z, u was c. This is ISS, if and only if there exists a function Vx, which is like a Lyapunov function. This function is bounded from below and from above by class K function. So the standard bounds, upper and lower bound, these are class K functions. They're function that, actually this is class K infinity that grows. So this is a function which is positive, definite, and proper, or positive, definite, real, and bounded, whatever you want to show. A function like this is like in Lyapunov theory, and dv dx. If the system were autonomous, we would write fx here. The system is not autonomous, we have xu. This is bounded by a decaying function of x plus an increasing function of norm u. That's it. So this is the Lyapunov-Sontag test to check this property. It's amazingly simple. And if u is equal to 0, this is reduced to the standard theorem of Lyapunov. And a consequence also of this is that from alpha and sigma and this, we can determine gamma also. This gamma here, this gain function, can be determined looking at these bounds here. So there is a test that does not require computing solutions, as it is the case for the Lyapunov test. Okay, this is an entire chapter. Our chapters in books now, you can be interested in reading. A final definition which is important. A system is strongly and also locally exponential in minimum phase. This notion, we will use it later on in the second part. If it is minimum phase, if it is strongly minimum phase, and in addition, this locally, beta and gamma are functions of this type. Beta is exponentially decaying. So beta RT is a number times R times this. So beta is exponentially decaying, and gamma is linear. So these are, in general, it's not guaranteed that we have a system like this. that these functions have these properties. So this is a kind of reinforcement of the property of being strongly minimum phase. But this is needed if we want to have asymptotic stabilities in certain circumstances. Okay. Okay, so why are we interested in minimum phase properties? Well, this comes from the from the theory. If we have this control here, we have this system. Now this system is the X system drives the Z system drives the Z system. So if the system is strongly minimum phase, this upper part is input to stay stable. This system is stable, and there is a well-known result that says that the cascade of a globally asymptotically stable system and an input to stay stable system is globally asymptotically stable. So the result, the system that we obtain is guaranteed to be internally stable. But we need this kind of strong property, strongly minimum phase. So let me repeat, if I use this naive control, and if the system is strongly minimum phase, then when I use this control, I get a system which is externally linear, internally is globally asymptotically stable. And this is why the notion of strongly minimum phase is important. Okay, I think this is probably summarized here. Again, the result is fragile, is not robust, because it relies upon exact cancellation. So I'm keeping the caveat that I read before. If we have, can we make another 10 more minutes, or are you tired? I can make a break now, but probably makes more sense. It's up to me. Okay, so I would like to mention, even though this is kind of last-minute story, I would like to mention all the theory that we've seen so far is relative to single input, single output systems. So the question is, can we extend this to multi-input, multi-output systems? The answer is yes, and there are some nice features that have been discovered in very recent years. I will not spend more than 5 minutes on that. For instance, let's consider a case of two input to output system for simplicity. There is a theory of normal forms that is analogous to the one that we have seen so far, and for a two-input to output system, the normal form will be like this. There are a string of integrators, and this is like the Q and B that we had before, but then this for the input Y1 XC11. But then for the input Y2, we have a string of integrator, but then from a certain point on, this term here pops up. So it's kind of a little sophisticated. But fortunately, and pops up through a function that depends on X. One can prove that if the system is invertible, and the inversion algorithm, which I had no time to discuss, has no singularities, then this form is necessary. So one can develop sophisticated normal forms also for multi-input, multi-output system. And the feature of this form, I put in red and blue the special feature. The fact is that this term A, the last row of the first string, pops up also in the second string, and also that these functions depends on X, but they depend on X in a special triangular form. Here, Z2 under bar is the collection of all the Z2 up to the value R1. So here we allow all the component of X1, but only the component of X2 up to R1. Here, the second we have all the components of X2 up to R1 plus 1, and so on and so forth. And here we have X2 R1 plus 1. So it's a very sophisticated way. And the interesting feature of this form is that if we have this, we can easily linearize the system using feedback and dynamic extension. And this was the result that was known since a long time, but never related to normal forms. But it's important and easy to relate it to normal forms. This matrix is non-singular. The matrix here is non-singular. The matrix consisting of B1 and B2 is non-singular. So we can implement this feedback law here, A plus BU, which in vector notation I write as a vector A plus a matrix B times U equal V, is the same as the feedback law that we saw before, is the multivariable equivalent of the feedback law. That we had in the previous slide, Q of zig C plus B zig C U equal V. In the multivariable case, we have a similar expression, which is this. And if we implement this feedback law, then the normal form greatly simplifies. Remember, this is a naive feedback law, because if we want to implement this feedback law, we should know exactly B and A, because it takes cancellation. So it's naive, non-fragile feedback law, but this can be fixed. So if we choose this feedback law, we get a system like this, which is somewhat simpler. But still we have these bothering terms. We have V1 here, V1 here, V1 here, delta. The fact of the bothering term can be suppressed if we take dynamic extension. Here we have the story of the zero dynamics, which I will skip. Again, it's not so difficult to skip, because the normal form is this. So if you want to find the zero dynamic, we set y1 equals 0, y2 equals 0. If we set y1 equals 0, y2 equals 0, everything will be 0. And so necessarily we have this. The u is B inverse, because this will be 0. And this will be 0, and this will be 0. So u will be the result of this. So this is the zero dynamics for a multi-input, multi-output systems. And again, we can say the system is minimum phase, globally minimum phase, and so on and so forth, as we had before. So we can extend these concepts. But the interesting feature is that if we look at this system here, we can make it linear by adding extra dynamics and then using an extra feedback. And the addition of the dynamic, here they have a chain of R1 integration between Y1 and V1. Here we have a sort of R2 integration between Y2 and V2, but there is troublesome term V1, V1. So if we call V1 the output of an extension, if we call V1 equal eta 1, and then we have eta 1 dot equal eta 2, eta 2 dot equal eta 3. So if we add a string of integrators on the first input channel only, so the idea is like this. So we have our system. We do the preliminary change of variables, use it here. So we have a system like this. We have here V1, V2. Here we have Y1, Y2. And we add a certain number of integrations on the first input channel. And this is V1 bar. We neutralize the effect of this V1 here, because V1 will be the state of the extension. V1 dot will be another state of the extension. As we neutralize the effect of these terms, and eventually, with input V1 bar, V2, then we have equal strings of integrators. And this is what is explained here. This is dynamic extension. And an easy calculation shows that the derivative of y1, y2 up to order R2, which is the higher of the two, is a affine expression of the V1, V2. This matrix is non-singular, so it can be inverted. And therefore, we can feedback linearize the augmented system. And here is the final result of this part, I think. So we have the original system. With the first feedback, we neutralize, we cancel out this term here. We cancel out this term. So with the first feedback, we end up with this. Then we add a dynamic extension, which is this. Then the resulting system with input V bar is feedback linearizable. So we use this feedback linearization. Essentially, we cancel out this term. Again, we make it equal V hat. So in 3 steps, from here to here, we get an input-output linear system. And if the zero dynamics were strongly minimum phase, then we get external stability. So this is a general design paradigm that works for general multi-input, multi-output systems, so long they are invertible and the inversion algorithm has no singularities. So this was discovered very recently, and the construction is fragile because this is a cancellation, this is a cancellation. And in the paper that I just learned yesterday will be published, we have shown how to make this robust. Okay, so this, I think, finishes this part 1, and I believe that I have calculated correctly the time. Yeah.
In linear systems, the notion of relative degree is not a simple set of integers, as you know. There's a notion of the matrix, zero dynamics of infinity, and
Yes.
and so on. So what you're making some assumption that the interactor is diagonal or something like that?
No, the story is that really
What is the definition of relative degree for nonlinear systems? Does it involve the matrix?
the nonlinear system, as in the case of linear system, not all systems have a vector relative degree. So having a vector relative degree means that essentially a nonlinear system will have a vector relative degree if these terms are all 0 and the matrix B1, B2 is invertible. Yes. This construction works also for the linear case. In the linear case, in general, we expect a structure like this, and if these terms are they will be constant in the linear case. If these terms are non-zero, the system does not have a vector relative degree. The high frequency gain matrix would be singular. If these are 0, we remain with B1, B2, and if this is non-singular, then we have a vector relative degree, which means... Pardon?
Linear systems always have relative degree. Now you have an interactor matrix.
Yes, but interactor matrix could be singular, yes. Yes, the interactor matrix could be singular. But you can make... the Ri here are the structure at infinity. The Ri here. And they coincide with the relative degrees if this decoupling matrix is non-singular. So the Ri coincide precisely with the degrees of the order of the zeros at infinity. If the system, imagine the linear version of this. The Ri will be the order of the zeros at infinity. If the delta are 0 and the B1, B2 is non-singular, then the coupling matrix is non-singular, and the system will have a vector relative degree. But the next passage says that if the system does not have a vector relative degree, then using dynamic extension can be turned into a system having a vector relative degree, all even or equal.
There's a result, that Jessica result, that you can always bring and sync because
Yeah.
you can always bring multiply, as you said, make an interchange of coordinates,
Yes.
diagonalize the interactor. Can you do something like that in nonlinear case?
This is what, essentially, this is what done, because, if you do this, essentially is, in that case, which Only recently was understood to be the general case for multi-input system. This scheme exactly because you have a preprocessor here. Then you have a dynamic extension, then another preprocessor. Then from here to here, the coupling method is diagonal. Also 1, 1, 1, 1, 1. So this is the construction. But the construction is fragile because the construction in the case of requires knowing the state and requires a lot of cancellation. And thanks God, recently it was understood how to make robust this and this. And this is even more subtle to make this robust. Robust in the sense that we were discussing before, and then I will explain it in the next, after the break. No, this is the last minute. With one, we essentially ended here. Day one, yes. But then here, this is the last minute of work. Okay, so good time for a break. 10 minutes break. We still have a lot of things to see, so it's only 10 minutes.